Today we will continue our discussion on the array level design issues. So we will talk about the bank organization, and then we will introduce this NVSim simulator, which you are going to use that for your homework 5. So basically, if you look at how we organize the memory into the bank, then we could have several levels of the hierarchy, right? So here we could have the subarray, which is usually the smallest unit array that you do not have the, let's say, partition of the word lengths and bit lengths. Of course, the definition of those, levels could vary depending on different technologies. But basic idea is that you have the hierarchy, right? So smaller array and then multiple of them become a larger array. So here in this particular definition, then we will assume the lowest level is a subarray where you can have, many word lengths, bit lengths, depending on your memory type, right? So the SRAM typically smaller array subarray size. As you go from the SRAM to the DRAM to the NAND flash, then the subarray size will increase. So here the multiple subarrays will form this, in this case, mat, and multiple mats will form a bank. So here, this is the definition in this particular hierarchy. In general, you will have like at least 2 levels of the hierarchy, up to 3 or even 4 levels, depending on the memory technologies. So here then, the general design consideration is that given the same capacity of the total memory array, then how do you partition that? Let's say each subarray become larger, or design it smaller, right? So there will be the trade-off, right, between those two cases. Even though the total number of bits are the same, then here you can tell, right? So if you design each subarray larger, then this is more area efficient because you are going to share more of those peripheral circuits like decoder, NVSim, and so on. So the area efficiency will be better, right? Because around those subarrays, then you have those peripheral circuits, then those could be shared more efficiently. But then the larger subarray will mean slower access, right? Because the word length and bit length will be longer, so RC delay, right, for the signal to propagate through the word length or bit length will be slower. So then this is a fundamental trade-off between those two cases. As you can imagine, right, for the faster memory, like SRAM, low-level caches, then you want to design smaller subarray size and then partition that into more units. And then for the DRAM or NAND flash, you want to have this as large as possible, assuming you satisfy the timing requirements. Then you want this as large as possible. So that many design choices, depending on the application and depending on the memory's technology. So here also, even within this kind of hierarchy, you can have different numbers of the activated mat or subarray. So here, when you fetch the data, right? So for example, the DRAM, then for example, you fetch the data, you do not need to access the 64 bits from the same subarray. You may, partition that into different subarray. So each subarray will give you certain number of bits, right? So this will be the activated subarray. So when you fetch the data, you active only a small portion of that, okay? But you are going to aggregate the data through the data bus, right? Through the data bus. So then we can define how many active subarray or submat or mat within the bank. So then this is a design choice. So here then we talk about the data bus, okay? So here then a typical routing for the data bus is this H-tree routing. It's like H shape. So here you have the global bus, right? And then you are going to split that, and then further split. So it's like H shape. So in this case, we call it local sensing because each subarray will have its own set of sense amplifiers. You are going to sense the data at each subarray, and then you digitize the output, and then aggregate the bits, right? So of course, depending on the architecture design, you may only need to activate one subarray or two subarray, then the others are idle. You only fetch the data from those two, if that number of bits can satisfy your bandwidth from your I/O. So here, then those sense amplifiers are local to each subarray. And then that means after sense amp is digital signal, right? Before sense amp, you know, it's whatever analog voltage on the bit line or current from the bit line. So after that will be digital signal. That means it's a full swing. So in this case, for example, each subarray will get like 8 bits, and then 8 of them, right? In total, we get 64 bits. So this is like a H-tree routing, and then is like a data bus. Okay. So then it could have another kind of architecture. For example, here, the sense amp could be shared between subarrays. So in this way, you can save the area for the peripheral circuits, right? So that means before the signal goes to the sense amp, then it's a partial swing signal, right? It's not fully digital. It's some analog, either voltage or current. So then you're going to have the analog signal going through this kind of long wires. Of course, then that may have some, you know, side effect like distortion or RC delay for this analog signal along those wires. But the benefit is to save the area because now you only need, you know, 2 sets of sense amp in this case. So this could be applied to some of those architecture design. Of course, depending on your design, let's say priority, whether it's area efficiency or you want like signal integrity or speed, right? So we will just use one example to illustrate the design considerations for the array level architecture. So here what we are going to show you is a prototype chip. Actually, this was from 10 years ago. So when I first started teaching this memory course, this is, you know, brand new at that time. It was published in ISCC 2013, and then there's a follow-up JSSC journal paper on that. So at that time, still, you know, it's Sandisk. Later Sandisk, you know, acquired by Western Digital, but this is still Sandisk at that time. So here, at that time, Sandisk was developing the RRAM technology in the cross-point manner. Okay, it's not the 1T1R we talked about earlier. So actually, they demonstrated this 32 gigabit RRAM chip is a cross-point array chip. So this is like the structure. It's like the 3DX point. The only difference is that here, instead of the phase changing memory, so here it has a selector and then a RRAM, a resistor. So of course, they didn't disclose what material is used for this memory element. So they just say this is metal oxide, Me. There's no like element as Me. Me means metal. Okay, it's just a generic symbol. But anyway, so the total die size 130 millimeter square and interface is NAND compatible. Okay, that means this is SNO. Okay, SNO IO. Page size 2 kilobytes. Okay, it's pretty slow actually, because it's NAND compatible. You see the rate latency in like a 40 microsecond. It's like the NAND speed, right? Then you may wonder, okay, why? I mean, as RRAM supposed to be faster, right? But why would this chip only, have the 40 microsecond read speed? So we are going to discuss why from analyzing the peripheral circuits from the next few slides. There's a reason behind. So the RRAM, I mean, the memory cell is fast, but then the array design makes this prototype pretty slow. Okay. So anyway, so here you see that this two-layer actually is a two-layer RRAM cross point and integrated at the top of the interconnect. So here the pitch is pretty small. I remember it's like it says 24 nanometer. So the half pitch, this is F in here. Each like F, this F is really like 24 nanometer. Okay. It's half pitch because pitch is here to here, and then wire is half of that. 24 nanometer is pretty small, so that's why in this cross-sectional TEM image you see that this is very small. Okay, and then you look at the CMOS circuitry. That means the peripheral circuits actually is hidden underneath. So you see those transistors are pretty large, right? So then I would suspect those transistors are at 180 nanometer or 130 nanometer. Of course, they didn't disclose what CMOS technology they use in the paper, but I would suspect it's old technology because here from the dimensions, you can see those transistors are huge. Okay, so this means this is supporting circuitry. That means peripheral circuits, right? Fabricated in very old CMOS. Okay. And then at the back end, it integrates very advanced small RRAM corresponding array. You see that this is a fundamental mismatch, right? Of course, this is a prototype chip, and the Sandisk as a memory company does not have advanced logic process, okay? And also as an early prototype, then they use some baseline, CMOS, which is at older nodes. Okay, so that's a background here. And then here you see how they organize this into the different levels of the hierarchy. So it has 16 bays. So each bay basically you can think is a bank in this case, different terminology, but it's the same thing, right? So it has 16 bank. And then each bank has this 32 block. You can think it's like a mat, okay? And the one mat actually under that is a very large. Actually, that mat is the same as a subarray. It only has 2 levels in the hierarchy. Okay. So here you see that each block here is like 2 kilo VRLAM. 2 kilo bit LAN, 4 kilo VRLAM, and then you have 2 layers. So then it's pretty large in terms of the subarray of size. And then, so here, in total, you have this 32 blocks times 4. So in total, you have like 128 blocks. So you multiply those numbers, it will give you this 32 gigabits. Okay. So here then, yeah, so more details, as I said. So 128 blocks. Okay, each block is this size. So here, but the thing is that you see here, each bay, or let's say each bank, has 64 amp. Okay, so you see that each bay here has only 64 amp, but actually here the entire bank has 128 blocks. Okay, so 128 blocks. Each block is so many bits, but the number of amp is very limited. You see here. This is unlike the SRAM or the DRAM design you have seen before. Even each bit LAN, you have 1 amp, right? So here, if you have each bit LAN 1 amp, then you have like 2 kilo in one block, or even 128 times 2 kilo for one bank if each bit LAN has its own SenSamp. So that means here this is not local sensing. Okay, this is shared. The SenSamp is shared across the entire block. Okay. So then it says 64 SenSamp, and then you have 64 like buffer after the SenSamp, which is a register. So only 64 bits will be simultaneously, sensed, accessed. Okay. So, but one page size is 2 kilobytes. That is the external I/O buffer size. So every time you still transfer one page. So that means you need multiple cycles to, fetch the data from the blocks to the page buffer, which is going to be sent to the outside, right? So that's why it's slow, because it has limited number of the SenSamp, and then you have this non-local sensing, and then you have to use multiple cycles to read. But the fundamental reason I think here is because the logic process, as I mentioned earlier, is an old technology node, right? So you see that transistor is huge, and then your memory is pretty small. So, even one subarray, you do not have too much space to have this many of those transistors underneath, right? Because memory is pretty small. The preferred logic transistor is very large, right? So when you design one SenSamp, that SenSamp's area could, relatively speaking, be much, much larger than the memory cell size. So that's why one block cannot have so many transistors underneath, because each transistor is huge, relatively speaking, compared to the memory cell size. So then you see this is a limitation in the design. That explains why this is a kind of slow.
This is what is called as block, was called as subarray.
Yeah, as I said, so the terminology could be different by different designs or different papers. So, but basically 2 levels in the hierarchy. They call lower level block, higher level bay. You can call it lower level subarray, higher level bank if you wish. Doesn't matter. So here then it shows some details of the peripheral circuits. In this case, the SenSamp. So here it has this, I believe, voltage mode sensing. So you have this cross-point array, and then you have the read voltage. And then you have to apply this read voltage here. And then I would say this is selected cell. Then depending on this, you have to also bias. This is exactly the same as one of the slides we showed earlier in the cross-point array. When you read the cross-point array in parallel, you have to use this. If it's voltage mode sensing, you have to use this kind of bias. Okay. So this VUB could be like a ground. Okay. Or some other common voltage. But anyway, so here you have to pre-charge here to be V-read, and depending on the resistance here, you are going to discharge here fast or slow. And then for other rows, unselected rows, you have to bias this to be V-read to minimize the leakage through the other cells. So here then this V-read is provided. Of course, here we have to share the SenSamp, so you have the marks to select. And then from the SenSamp, then we have this V-read voltage and pre-charge to here, to this node, which will be connected to here. And then you will have this, through this follower, you are going to have this voltage also decay, depending on the voltage here. Then that is to be sent to this comparator to compare with the reference voltage, depending on the decay rate. Right? Strong cell means no resistance cell, then you are going to have decay fast. And then weak cell means high resistance state cell, you decay slower. So then here, depending on the, after you enable the SenSamp, then you're going to compare this voltage versus the reference, right? So the sensing time is slow for this case. Okay. This is about 1 microsecond. Yeah. For sense one cell. But as I said earlier, to fill in that page buffer, you need multiple cycles because every time you only can get 64 bits, but you have to repeat this for many cycles, so you can fill the entire 2 kilo number of bits. So that's why the total read latency is about 40 microseconds. So that's why this is a NAND compatible in terms of the I/O interface. So any questions here? Of course, this is some like exercise. This prototype never fly after that. So Sandisk dropped the RRAM development. But this was quite an accomplishment at that time, 10 years ago, like 32 gigabits. So even though the performance is not that impressive, right?
Since AMP is improved, then the when can we see?
Yeah, I mean, if you improve some design, use more advanced technology node, then you can improve the overall design. You have more parallelism, you can improve the speed and so on. Yeah. Okay, so then the next topic, this NVSim simulator. So why do we need the circuit level simulator tool? Because here for the memory array architecture design, there are so many design options. And we have to trade off those metrics, right? Like area and then speed, power consumption, like including the dynamic read and write power, and also the standby leakage power. So then we need some like a fast estimation tool to do that job, because you cannot generate the detailed layout for each technology if it's at early design stage, right? So you want something fast because it's not every technology would have the memory compiler available, right? So in the early stage, you want something that could quickly estimate the design options. So there was some early work in this field. Even back into the 1990s, there was a tool called Cacti. This was originally developed by the HP lab, Hewlett Packard. This was mainly used to estimate the SRAM-based cache. Later, they extended to the embedded DRAM, the 1T1C embedded DRAM based cache. So the original developer of this Cacti is Long Jupi, Dr. Long Jupi from HP Lab, which later joined Google and designed the TPU. He was the first author of the first generation TPU and presented in ISCA 2017. But before that, he was with HP, and his major contribution to the field is to, develop this Cacti. And then there will be like an extension follow-up work inspired by this Cacti, okay? But then this Cacti is mainly for the SRAM or EDRAM-based cache. There's no tool for non-volatile memory because we have so many emerging non-volatile memory. Back in 2010, around that time, then emerging memories like RRAM, MRAM, phase change memory just started. Of course, this started a few years earlier, but at that point, then there is a need to evaluate those non-volatile memories as well. So that's why here Professor Yuan Xie's group developed this NVSim non-volatile memory, right? Non-volatile memory simulator, NVSim. So it follows the Cacti models for the SRAM, DRAM, EDRAM, and then it adds more modules to predict the non-volatile memory. So Professor Yuan Xie was with Penn State University at that time when he initially developed this NVSim, and later he moved to UC Santa Barbara, UCSB, and recently he moved to Hong Kong UST. But anyway, so this was developed by Professor Yuan Xie's group. And here we have shown this kind of subarray level architecture earlier. So basically, it models all the peripheral circuits, and then it can generate the PPA, the power performance area for those modules, and with different technology nodes and different memory types. I would say this is not spice simulation. This is not synthesis. This is not memory compiler. Okay, this is analytical models about the delay, power, area, and so on. So that's why it can run pretty fast. This was written in C++, but you can write in Python, doesn't matter. So it does not require EDA tool. Okay, it's just some simple scripts. But it does model different design options. Okay, for example, for the transistor, if it's embedded with the logic, then the logic could have high performance transistor, low power or low standby power transistors. So the like the VTH, on state, off state, currents are all different, right? And then the sense amp, right? We have the current sensing, voltage sensing, and we have the analytical equations discussed earlier, right? For the sensing speed, the delta T, right? Depending on the node resistance and also the cell resistance, the wire resistance, wire capacitance, and so on. So you have some equations you can use. And then here the array could be, here the MOS access means 1T, 1R, like 1T, 1R, and the cross-point array, right, with the selector. And the driver we discussed earlier, then you can optimize for area efficiency, you can optimize for the latency, and so on. So you have many options. So if you multiply, let's say each of those modules have like 5 options, and you have so many modules, then you 5 times 5 times 5 times 5. In total, if you just combine all of them, it could be in the hundreds or even thousands of configurations, right? So we want to understand the design space. That's why we call design space. Before you do the real tape out, as architect, if you have like a higher level design, you need to understand the design trade-offs before you implement into the silicon. So that's go for this tool. So here, as I said, it's based on some analytical equations, but they did some validation with the real chip. So here, for example, they compare their prediction from the analytical models with the ISCC papers. For example, at that time, 64 megabit MRAM, right? The total chip area, latency, and so on. Of course, there will be some errors because it's not accurate spice simulation, but it gets close to the actual numbers from those test chip, right? So here another example with this phase change memory, 512 megabits at that time. So as I said, the tool was developed around like 2010 to 2012, around that time. Okay, about 12 or 14 years ago. So here I just show some examples. How are we going to use this for design space exploration? So here, assuming we want to design RRAM-based last level cache, of course, the underlying assumption is not a good assumption here. But assuming you want to do this job, then how you are going to use this tool? But let me ask you why this is not a good assumption. Okay, RRAM based on last level cache. We haven't talked about RRAM in great details, but I would say the starting point is not good. Any idea? Why?
maybe because like your RAM is slower than DRAM, like how we saw
Slower than DRAM?
in the example that Sandisk made, right? So
And this one is not Sandisk. Sandisk is a special case, but in general, RAM speed is like a few nanoseconds, not 1T1R. Let's say no problem. Okay. So RAM has endurance problem. We haven't talked about that, but it's like flash memory. You cannot cycle it many times. Okay, but for NAS level cache, you rewrite very often. So the endurance will not be enough. Okay. But anyway, if this is the task we are going to do, then you can use this tool to evaluate the design options. So here, for example, at that time, we choose the technology node, 32 nanometer at that time. Okay, this was, 12, 14 years ago. Let's say our goal is to design 8 megabytes cache. And then, cache has this associativity, like 8-way, okay? So then you are going to look at the design options, okay? Or let's say optimization targets, whether you want to minimize area leakage or you want to improve the speed. So you can have different design points in this like 3D plots, depending on the, let's say, the metric you are going to optimize for, like the latency, chip area, leakage, okay? So then here, this is the design options you are going to vary in the model. So as I said, so here you can change the subarray size, how many subarray, and then the IO bandwidth, and then let's say IO width, number of bits in parallel, and then the let's say the wire model, local interconnect, global interconnect, and transistor model, high performance, low power. And here, of course, you are given the task to do the RRAM, but in general, you can vary that. And then the driver option, and then you do the current sensing, voltage sensing, and so on. So you have so many choices, okay? So you can vary or sweep the parameters in the tool. Then you can generate the design space. So this is how it look like, the design space, because you have so many combinations, right? So each point here correspond to one particular combination of the, let's say, the number of cells in one array, and then the transistor type, the driver size, and so on. So you have hundreds of points. So you see that here, in general, right? At the same technology node, then the RRAM, of course, is smaller in cell size compared to the SRAM, right? SRAM 6 transistor, RRAM 1T1R, right? So that's why the memory density, you see the pink, which is SRAM baseline, is mostly here. And then the RRAM density will be better at the same technology node. I have to emphasize. Because at that time, there's no 3 nanometer SRAM, right? At the same technology node, 32 nanometer. So then the, let's say the 1T1R RRAM and then correspond RRAM, then of course the memory density could be higher. But you also see the latency is higher, right? So here, you want this corner, okay? Higher density, but lower latency, okay? You want this corner, okay? So that's the like envelope, right? You're looking for along this direction. And also here, in terms of the write latency, right? Also slow, right? Let's say the RRAM compared to the SRAM, right? So you can say that in general, you have the trend. But if you want to pick particular design points from that graph, then you can have those different design points. For example, if you want to do the area optimization, that means the smallest area, you pick the point that is from this, let's say, highest density. Then if you look at the area, yeah, it's smallest, but then you can see the latency is pretty long, right? Like more than 100 nanosecond even for this corresponding array. And then in the array size 512 by 512, you have to use non-H tree because you can share the same sample and then save the area, right? But at the expense of longer latency and so on. But if you want to optimize for the read latency, okay, you have to increase the size significantly. And then latency could be below like 2 nanoseconds. And then you have to use H tree, smaller subarray size, and so on, right? Depending on your target. I will not, go through the entire table. Basically, you can optimize for your design targets, right? That means your configuration will be different for different design targets. So then this is at the bank level, okay? You have the 8 megabytes SRAM cache. And then usually when you talk to the computer architects, they want to understand the system level impact. So that's why usually they have to couple this kind of simulation to the Gen 5 simulator. So if you have ever taken the computer architecture courses, I don't know in Georgia Tech if they, use a Gen 5 for the lab project or not. But if you go to the computer architecture community and look at the papers from the ISCA, HPC, Micro, and so on. So when they benchmark the CPU workloads, especially with different cache design, they will use this Gen 5 simulator. And it's a cycle-accurate trace-based simulation. It will analyze the data access pattern, how many reads, how many writes, depending on your workloads, applications. Right. So anyway, so you have to configure the entire CPU configuration, like architecture. So in this particular example, let's say we now design this L3 cache with RRAM. Now we want to evaluate if you plug in this into the CPU, then what would be the CPU performance? Okay. So then you have to define the CPU like a spec, like a clock frequency, 32 gigahertz, and then 8 core, multi-core. And then you L1, L2, L3 cache, each level, the capacity, and then you use SRAM or RRAM. Of course, we know, I mean, for sure, L1, L2, you don't want to use RRAM because, you need the speed there. But anyway, as an exercise, you can include the RRAM options there. Later, you will see the trade-off. But anyway, you define all those L1, L2, L3 cache technology, and then the capacity, and then the associativity, and so on, okay? But then the latency and area, the PPA, come from the NVSim simulator in this case, okay? In Gen 5, you only define those parameters, like the cache hierarchy. Okay, so if you do that exercise, this is, again, you have many design points. So that will become some envelope in this trade-off. So what you care about here from the computer architecture standpoint, this is the indicator for the performance, the instruction per cycle. The CPU, operate on the ISA, right, instruction sets. So then how many instructions you can execute per CPU cycle? Okay, so that is the IPC, and the larger the better. So here you see that this is a trade-off with has trade-off with this dynamic power of the processor. So here you have different options. Let's say if you use a standard design, which is SRAM used for L1, L2, L3 cache, you have this one. Okay, so the IPC is the best. Still SRAM is fast. Okay, but then the dynamic power will be higher here. And then you see if you use all the L1, L2, L3 cache, all of them as RRAM, then it will be somewhere here. Okay, the performance is worst, but then the power could be minimized, but the performance is too bad in this case. So some combination in between, right? So let's say SRAM, L1, L2, and RRAM L3. So then this one could be a better trade-off, right? Of course, here you have different configurations there. So similarly, you can look at the IPC versus the chip area. Okay. So basically, this provides a benchmark all the way from the technology to the processor's performance under the workloads. Okay. So any questions here? Okay, so then here is the GitHub link for the NVSim, and this is a reference paper in the IEEE CAD journal. And in the homework, I already uploaded the version that you can run, okay, without downloading from here. And you can compile that and run that. So here then, let's take a quick look on the format of this tool. So here, what you could modify as a user is this sample configuration file. And then in this configuration file, you can define different design options, right? So you are designing cache or RAM. In cache, you have this associativity. In RAM, you don't have that. And then you can define your optimize, because it will actually search for you. It has so many like design points. If you specify the design targets, it will pick the best read latency design option for you. Okay. And then you define the technology node, define the bank size, and then the I/O width, how many bits you want to get from the I/O in parallel. And then the transistor, like technology, high performance, or low power, or low standby power, and then the wire type, and so on. Okay, so many like options. But anyway, so in your homework, we'll provide you the cell level STT-MRAM parameter file. Okay, you can modify that, and then you will see the impact of the technology, the cell, the memory cell, to the performance at the bank level. And then you define how many bank, how many mats become one bank, how many subarray become one mat, and so on. And then you have the max, how many colon share one SenSamp, and so on. So I believe in your homework, you only need to modify the cell, okay, the parameters there. But if you wish, I mean, you can have a try to modify other, design options. So here, this is the cell level parameters, right? For example, this MRAM, and the cell area, like in terms of F², close to 60. And then the on-state resistance, off-state resistance, on-off ratio is pretty small. If you recall, we talked about STT-MRAM earlier. And sensing is current mode, and the other parameters like the read write conditions, like the current, and then the pulse width, and so on. So you can modify depending on your technology, right? So this foundry may have this particular, parameters. The other foundry may change those numbers. So then after you run the simulation, this is the sample output. So you're going to get this kind of output. First of all, it will repeat your inputs. So this is just a log file to basically record what is your inputs. It will show your inputs first, like those design options, and your design spec. It will just show you what you have put there, and then the configuration. It will show you what kind of bank organization, mat organization, and then all your design options you specified. Then finally, it will show the results, right? The total array, the bank area, and then it will have the breakdown into each match and subarray, and then array efficiency, right? And then the total like read latency, and also the breakdown, right? How like decoder and the sense amp, bitname, mux, and so on. So it will have some breakdown of the latency. So yeah, you can continue this result section. It's just a snapshot. So basically, this is the NVSim simulator, and you're going to use that for the homework. Just a few more words. I didn't talk about the NeuroSim, which is my lab's tool, which extends from this NVSim actually. But we incorporate the in-memory computing into that, because NVSim is only for the memory in like regular memory access. There's no in-memory computing capability. So our lab extends the simulator as NeuroSim, so we can, search for the neural network acceleration. And also another, let's say, extension done by our lab is to support more advanced technology nodes and more memory types. The reason is that here, as I said earlier, this was developed like from 2010 to 2012. So then the CMOS logic transistor process at that time, right, maybe 32, 28, 22 nanometer. So there's no support for more advanced technology nodes. That's why we extended the roadmap for the technology, for the logic, to today's, 5 nanometer, 3 nanometer, even futures, 2 nanometer, 1 nanometer, and beyond. So that's why I think I suggest you to watch my recording lecture, right? The research presentation while I was traveling last week. So you can get better ideas what we have there for the NeuroSim. But anyway, for this course, we will just rely on this NVSim, and you are going to practice that with your homework. Okay. So, any questions here? If no, then we can stop earlier today.